Welcome back to Agentic AI World. This is episode 10, and we're going big today. The topic is Design ChatGPT from scratch. This is one of the most impressive system design questions you can face in an AI interview. And if you can nail it, you'll stand out from virtually every other candidate. Let's get into it. First, let's frame the problem. We're designing a system that can engage in natural, helpful, and safe conversations with millions of users simultaneously. It needs to handle diverse queries, from writing code to explaining quantum physics to drafting emails. It needs to respond in seconds, scale globally, and do it all while avoiding harmful outputs. That's a massive engineering challenge, and we need to think about it from both the ML and the system's perspective. Let's start with the foundation, the transformer architecture. The backbone of ChatGPT is a decoder-only transformer. Unlike the original transformer paper, which had an encoder-decoder structure, GPT uses only the decoder side. The key components are token embeddings plus positional encodings, multi-head self-attention layers, feed-forward neural networks, layer normalization, and a final output projection layer that maps to vocabulary probabilities. In the self-attention mechanism, each token attends to all previous tokens in the sequence. This is called causal or autoregressive attention. The attention formula is softmax of Q times K transpose divided by the square root of the key dimension, multiplied by V. Multi-head attention runs this in parallel across multiple heads, allowing the model to attend to different types of relationships simultaneously. For positional encoding, modern models use rotary position embeddings, or ROPE, instead of the original sinusoidal encodings. ROPE encodes position information directly into the attention computation, and it generalizes better to longer sequences than the model was trained on. Now, tokenization. You don't feed raw text into a transformer. You first convert it into tokens using a subword tokenization algorithm. ChatGPT uses a variant of byte pair encoding, or BP. The tokenizer learns a vocabulary of common subword units from the training corpus. Typical vocabulary sizes are 32,000 to 100,000 tokens. The trade-off is that larger vocabularies mean each piece of text requires fewer tokens, but the embedding matrix gets bigger. In interviews, mention that tokenization choices affect multilingual performance. BP trained primarily on English text might tokenize other languages inefficiently, requiring more tokens per word, which increases cost and reduces effective context length. Let's move to the training pipeline, which has three major phases. Phase 1 is pre-training. You train the base model on a massive corpus of internet text using next token prediction. The model sees trillions of tokens from books, websites, code repositories, and other sources. This phase is enormously expensive. Training GPT, 4-class models cost tens to hundreds of millions of dollars in compute. Key concepts for pre-training include the scaling laws discovered by researchers at OpenAI and others. These laws show that model performance improves predictably as you increase model size, dataset size, and compute budget. The chinchilla scaling laws suggest that for compute-optimal training, you should scale data and model size roughly equally. A 70 billion parameter model should be trained on about 1.4 trillion tokens. The infrastructure for pre-training involves thousands of GPUs or TPUs running in parallel. You use techniques like tensor parallelism, which splits individual layers across GPUs, pipeline parallelism, which splits different layers across GPUs, and data parallelism, which replicates the model and splits the data. Mixed precision training with FP16 or BF16 reduces memory and speeds up computation. Gradient checkpointing trades compute for memory by recomputing activations during the backward pass. Phase 2 is supervised fine-tuning, or SFT. After pre-training, the model can complete text but isn't great at following instructions. You fine-tune it on a curated dataset of prompt response pairs where human labelers write high-quality responses. This dataset is much smaller, typically tens of thousands to hundreds of thousands of examples, but it's carefully curated. Phase 3 is RLHF, reinforcement learning from human feedback. This is the secret sauce that makes ChatGPT feel helpful and safe. First, you train a reward model. Human labelers rank multiple model outputs for the same prompt. The reward model learns to predict which responses humans prefer. Then you use proximal policy optimization, or PPO, to fine-tune the language model to maximize the reward model score while staying close to the SFT model using a KL divergence penalty. A newer alternative to PPO is direct preference optimization, or DPO. It skips the explicit reward model and directly optimizes the language model on preference pairs. It's simpler to implement and more stable in practice. Mention DPO in interviews to show you're up to date. Now, let's talk system design for serving ChatGPT at scale. This is where the interview really gets interesting. The inference pipeline works like this. A user sends a message through an API gateway. The request goes to a load balancer that routes it to an inference server. The server runs the model auto-regressively, generating one token at a time. Each token is streamed back to the user via server-send events or WebSockets. Token generation is inherently sequential, which is a bottleneck. Each forward pass through the model generates exactly one token. For a 500-token response, that's 500 forward passes. This is why inference optimization is critical. KV cache is the most important optimization. During autoregressive generation, the key and value matrices for all previous tokens are cached, so they don't need to be recomputed at each step. Without KV cache, generation time would scale quadratically with sequence length. With it, each step is roughly constant time. The trade-off is memory. For a large model with a long context, the KV cache can consume tens of gigabytes of GPU memory per request. This leads to the memory management challenge. GPU memory must be shared between model weights, KV cache for active requests and activations. PagedAttention, introduced by VLLM, treats KV cache like virtual memory pages. Instead of pre-allocating contiguous memory for each request's full potential sequence length, it allocates fixed-size pages on demand. This reduces memory waste from 50 to 80% and dramatically increases throughput. Batching strategies matter enormously. Naive batching waits until a batch is full, which adds latency. Continuous batching, also called in-flight batching, adds new requests to the batch as soon as a slot opens up when a previous request finishes generating. This maximizes GPU utilization. Speculative decoding is another optimization. You use a smaller, faster draft model to generate several candidate tokens, then verify them in parallel with the large model. If the large model agrees with the draft, you accept multiple tokens in a single forward pass. This can speed up generation by 2 to 3 times with no quality loss. Model quantization reduces precision from FP16 to INT8 or INT4, shrinking memory requirements and speeding up inference. Techniques like GPTQ, AWQ, and GGUF enable aggressive quantization with minimal quality degradation. A 70 billion parameter model in FP16 needs 140 gigabytes, but in INT4 it fits in 35 gigabytes, running on a single high-end GPU. Now let's zoom out to the full system architecture. At the top, you have a global load balancer distributing traffic across regions. Within each region, an API gateway handles authentication, rate limiting, and request routing. Behind that, a conversation service manages chat sessions, storing conversation history in a database. The inference cluster is the heart. You need multiple GPU servers, likely NVIDIA, a 100S or H100S in production. Use a serving framework like VLLM, TensorRT-LLM, or TGI from Hugging Face. Auto-scaling based on GPU utilization and queue depth ensures you handle traffic spikes. For conversation storage, you need a fast database for active sessions and durable storage for history. Redis works for active session context, while a database like PostgreSQL or DynamoDB stores the full conversation history. Consider tiered storage where recent conversations are hot and older ones are archived. Caching is interesting for LLMs. You can cache at the prompt level using semantic similarity. So if many users ask similar questions, you serve a cached response. Prompt prefix caching reuses KV cache computations for shared system prompts, which is huge when many requests share the same long system prompt. Streaming is essential for user experience. Nobody wants to wait 10 seconds staring at a blank screen. Stream tokens as they're generated using server-sent events. The first token latency, time to first token, or TTFT, is a key metric. Users perceive the system as fast when TTFT is under 1 second, even if the full response takes 10 seconds. Safety layers are non-negotiable. You need multiple layers of defense. Input filtering catches prompt injection attempts and blocks obviously harmful requests. The model's own RLHF training provides intrinsic safety. Output filtering scans generated text for harmful content, PII, and policy violations. A moderation API, either built in-house or using services like OpenAI's moderation endpoint, provides an additional safety net. Rate limiting and abuse detection prevent misuse at scale. Content filtering needs to be fast since it's in the critical path. A common approach is a lightweight classifier that runs on each output chunk during streaming. If it flags something, you can stop generation immediately rather than completing and then filtering. Let's talk about cost estimation, which interviewers love. For a service handling 100 million requests per day with an average of 500 tokens per response, you need roughly 10,000 to 50,000 H100 GPUs depending on model size and optimization. GPU costs alone at cloud rates are enormous, which is why companies like OpenAI invest heavily in custom hardware and optimization. A rough estimate is 1 to 5 cents per 1,000 tokens for a frontier model. At 100 million requests per day, averaging 500 tokens, that's $500,000 to $2,500,000 per day in inference costs alone. This is why efficiency optimizations like quantization, speculative decoding, and caching are existentially important. Some advanced topics to mention in interviews. Mixture of experts, or MO, architectures like GPT-4 is rumored to use. Instead of activating all parameters for every token, Mo routes each token to a subset of specialized expert networks. This allows much larger total parameter counts while keeping inference cost manageable. Context window extension. Modern models support context windows of 128,000 tokens or more. Techniques like alibi, yarn, and ring attention enable training and inference on very long sequences. This is important for use cases like document analysis and code generation. Multi-modal extensions. ChatGPT now handles images and other modalities. This requires vision encoders like CLIP or VIT that encode images into the same embedding space as text tokens. The architecture adds cross-attention or simply concatenates visual tokens with text tokens. Tool use and function calling. The model is fine-tuned to recognize when it should call external tools, APIs, or functions. It generates structured output like JSON